guys, what we're going to cover in this video is a repeated measures ANOVA two-way with interactions. Sometimes these are called doubly repeated designs because the independent variables are both repeated. So remember that as we work with repeated measures data, we usually get it in long format or wide format where each person is their own row. So all of the columns are measures that we want to use. And we're going to have to melt that down into long format where we have one or more IV columns and one DV column. So we're kind of going to work this out though, because when you melt data, what happens is that all of the information in the repeated measurements get melted into one IV and one DV column. And that IV column has the conditions. So it's really tempting to take those conditions and just treat them as one giant IV with a bunch of levels. But the purpose of these designs is to investigate the interaction. So we want to make sure that we create two separate columns to accurately identify each IV separately and their levels so we can create those interactions. So remember, when we study the IVs by themselves, we're looking at those main effects. When we study the interaction, we're looking at the conditions, how the condition means differ versus how the level means differ. And so this chart is not a new one, it's the one we've looked at in all of the ANOVA analyses, but remember that if you have a main effect and you want to follow it up and levels are more than 2, it's going to be a dependent t-test, probably with a Bonferroni correction because it's the easiest one in R. That's the same thing for the other main effect. If the levels are more than 2, those levels are only 2, you're just going to interpret those means. You've already run that analysis, remembering that F and T are the same with only 2 levels. If the interaction is significant, 2 levels are not, you're going to split one of the IVs and then run dependent T on the other IV. And so this one's really easy in following up since everything is repeated, all the post hoc tests are dependent T's. Okay, so people often ignore those main effects because it will create type 1 error when you run all the main effects and all the interactions, and you sort of put this design together to investigate the interaction, so why would you ignore it? Okay. So we're going to use some data from my research lab where we're looking at kind of a family feud style design where people are asked, if I said lost, how many people out of 100 would say found as their first word? And the number is really high. So we're going to use our repeated measures 2 data, and what happens is that we have each item pair is related in 2 ways. So there's the forward strength of the item, which is how strong that relationship is between lost and found, and we've categorized that into low and high. And then there's the backward strength of that item, which is how related it is the other way around. So if I said found, how many people out of 100 would say lost? That number is different than lost to found. Okay? And so we've categorized that as low versus high. So those are the levels for each IV. When we get into the conditions, what ends up happening is we have low, 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 high, high, low, and high, high. So we've got 4 different conditions because it's a 2 by 2 repeated measures ANOVA. Okay. The dependent variable, since I've seen all 4 types of these word pairs, is just my rating of the word pairs. So we want to know, essentially, is there an interaction between the task we're asking you to do forwards and the sort of implicit backwards task that's also going on. Okay. So let's start with G-power here and estimate our required sample size, pretending we were just designing this experiment. Okay. So our test family, again, is an F test. Let me scroll down a little here. And our test is still repeated measures with n factors. So the repeated component of G-power is a little confusing, personally. What we're going to do is come over here and pick F test. Within repeated measures within. Right? We're going to estimate our effect size by clicking determine, direct, and entering a partial eta squared. Okay. Now let's see here. In this particular example, we did a small effect size. We're going to use 0.01 here. Okay. From there, I'm going to hit calculate and transfer to main. my other mouse so it's not so loud here. Our alpha is going to be 0.05 because that's our traditional PD criterion. Power is going to be 0.8, so that's 1 minus beta, which we traditionally set to 20%. Number of groups here is the number of IVs. Number of measurements here is the number of levels or conditions. We're going to work on the interaction, so we're going to use conditions here. So we're going to say 2 IVs and 4 conditions. We're going to leave correlation among repeated measures as 0.5. It's a good guess if you don't know. And we're going to leave our non-sporicity correction, epsilon, as 1. Okay. And so this does match our one-way repeated measures design. Okay. And then I set the correlation to be a lot higher in this particular example, but let's pretend like it's 0.5 for a second. And it says I need 138 people. If we assume the correlation among repeated measures is actually much higher than that, I only need 30. So that correlation does affect power quite a bit. Right? So we need a small effect size. We would need 30 people to find a small effect size with a very high correlation between measures. And in these studies, they tend to be very high. Okay? And the only reason I knew that is because this is research in my own lab. In your research, you would probably want to guess 0.5. Okay. All right, so we're going to flip back and forth here between R and the Word document. And so I just want to make sure that all of my data is accurate first. So I'm going to load that data set. So remember, when you set your working directory, this is going to be different for you, but this is where my file is hidden. And I want to use read.csv. I have a little note here about importing data sets, but if you use the import data set function, be sure you use the from text base option. Read.R tends to do some wonky things, and we've had some different issues with it. I know this is not the right file. R2, here we go. And it'll show you kind of what that looks like and all the titles and stuff, and so you can just click import and change the name of it. They had gotten rid of this for a while in Studio and they added it back, thank goodness, because read.R sometimes, God bless it, does some things that you don't want it to do and you won't realize that bad things are happening until it blows up. So we can always use read.csv here. And now we've got our data set. Okay. This data set is in wide format currently, where every person gets their own row. And there's some other columns that are used for a different example that we're going to ignore. So what I'm doing is I'm just dropping everything. So I've gotten rid of that other stuff I didn't need, but I already have a participant number, so that'll be useful later. Okay. Now for accuracy, participants were asked to rate this from basically 0 to 100, so I just want to make sure I don't have anything over or under that. So all my minimums look good, and then my maximums are not good. So I have one person here, but oh, that's the subject number, derp. So my max here looks fine, and then my maximums here look okay because they're less than 100. My fault there. Okay. So everything should be 0 to 100, and everything looks good so far. Okay. With that summary function, I can see I don't have any missing data, so I don't need to do anything with missing data. But remember, when you're working with 5% rule for missing data, you have to have at least 20 columns for that to work. So we would have to delete people anyway. We do want to screen the data set in wide format and run outliers here with Mahalanobis, because that will keep the correlation between peoples. Essentially, it will make sure that subject 155 here is subject 155 the entire time. You can screen in long format, but it's probably more appropriate, especially given the way Mahalanobis works, to screen them in wide format. Okay. So we want to make sure we know that person 1 is person 1 the whole time. So at this point, hopefully Mahalanobis is old news. What you're going to do is use the Mahalanobis function and fill in your dataset name here. But I want to make sure that I drop that participant number this entire time, because I'm not screening what participant number I gave them. So that's what my -1 here is. And if you're not sure what column number it is, don't forget you can use the names function. And it will show you the column names. Under summary works fine too, but subject number is column number 1. Okay, so that's all I'm doing here is dropping number 1 the entire time. So I have my Mahalanobis scores, but I don't really know what to do with them. So we have to create a cutoff score. Remember, our cutoff score is based on chi-square, so we're going to do 1 minus 0.001 because we're using this for the big important rule in our data screening lecture, and setting our degrees of freedom to be the number of columns we used for this particular analysis. And so we can run this code and see that our cutoff score is 18.47, and that used 4 columns, which makes sense because we have 4 conditions. The summary function here will tell us the number of people who are not outliers. And so true values are people whose scores are good, and false values are scores are people whose scores are outliers. So I have 1 outlier in this data set. So what we want to do is exclude those outliers by using the subset function in the same way as checking for them outliers. So we want to keep all of the people whose scores are less than the cutoff. Because remember, if they're greater than the cutoff, that means that they are an outlier. Okay, let's move on to our real assumptions now that we've cleaned out the inaccurate and outlier data. So the correlations in a repeated measures design, remember, is a special rule where we essentially want things to be super correlated, but they can't be perfectly correlated. So we do want high numbers because that increases power, as I showed you at the beginning of the video, but we don't want perfect numbers because that will make the analysis will not run. Okay. So we're going to use the core function on our data set. We don't need to drop the categorical column, or I'm sorry, you will need to drop categorical columns. You don't really need to drop subject number, but just don't look at it. Okay. And then we're going to use that symbols for numbers chart to help us ease seeing it. Okay. So in this example, I did drop it, but I'm mainly here looking for ones that are not on the diagonal. The ones on the diagonal are it's correlated with itself, and we do want that. So let's look at that here. I did drop my my subject number, which is not a categorical column, but it wasn't necessary. So our symbols for numbers here, I got commas, which means they're between 0.6 and 0.8, and a star, which means it's 0.9 to 0.95, but that's okay. And I can look at the whole thing if I wanted to use this for power. So I estimated the correlation between levels was 0.9. I really probably should have gone a little lower and used 0.62. So I could use that for my next power analysis for maybe a follow-up study. Okay, so our correlations look fine. All right. Scrolling through all this here, I just gave you an example of power that you could go back and test if you wanted. For purposes of the video, I'm going to kind of skip over that, but be sure to check your learning as you're going to make sure that you're getting the same numbers that I am, just to make sure that you get what's happening as we go. We're going to set up the rest of those assumptions by making a random variable and a fake analysis to examine the residuals, the standardized residuals. So if you need more on that, go back to our data screening lecture. And so I'm just going to make sure that I drop that subject number column. And so that's one reason why I left it in the data set, was so you could see if you had extra columns how I could work through this without like deleting them and adding them later. Right, so I'm setting up my random variable using the chi-square function, and 7, remember, is just in my magic number. You can do any number greater than 2, just so you get enough variance in your random numbers. I'm going to use my data set to predict that random number so I can look at the residuals across the data set. I'm going to standardize those residuals, aka z-score them, or we're going to studentize them so that they are on a scale that's easy to interpret. Do the same thing with my fitted values. Okay. So remember, this is random. You're going to get a slightly different picture than me, so let's look at normality. Okay. And my normality is a little skewed. We want this to be centered over 0. It's not, and mostly between 2 and 2, that is. Okay, so if I wasn't sure, I could run this again just to see another one. Now this one looks really nice. It's mostly centered over 0, and it's mostly between 2 and 2 with a couple of stragglers. And so like I said before, don't run this till you get the answer you want. Run this several times just so that you have like a kind of an overall picture of how this is going. Okay. Over a couple of runs, I can tell maybe a little bit of skew. Okay. If you're in my class and you're writing up this for an assignment, be sure that your answer matches the picture that you paste into your document. Okay. Let's look at linearity here. Okay. Linearity looks great. Between 2 and 2, the dots are on the line. Okay. Now onto homogeneity, a little bit of homoscedasticity too. What I've got here is mostly okay. So it's mostly between 2 and 2. 2 is probably out here, right here on the edge. Couple of dots here between 2 and 3. This way, not as good, right? So it's a little bit more more spread out on the top than the bottom. I would say this is mostly okay. Maybe some small problems with homogeneity. For homoscedasticity, if you wanted to look at that, it's a little problematic because it does start to make this sort of triangle shape where the spread of the dots is wider here than it is over here. Okay. All right, so we've skipped through all of this. There's more explanation if you need it. But now what we're going to do is look at Mauchly's. We talked about Mauchly's in the one-way repeated measures video. But essentially, it's a test for homogeneity for repeated measures, sort of. And sometimes it's called compound symmetry. What that means is that there's two parts that need to be symmetrical for sporicity to be met. And what that is that the correlation between levels is equal. So 1 to 2 is correlated at the same level as 1 to 3, and 1 to 4, etc., etc. Additionally, the variance of the difference scores between levels has to be equal. So what you do is you take 1 minus 2 and calculate the variance. Then you take 1 minus 3 and calculate the variance. And you compare those two variances. It is not the same thing as saying 1 has the same variance as 2. Now, it's often impossible to meet those standards depending on the design of the research study, because anytime you have a study that wants floor or ceiling effects, so for example, a weight loss study where you want people to lose weight, or a tutoring study where you want everyone to make an A, you can often decrease the variance as you go, which will usually violate that assumption of sporicity. So often people will ignore it. Now here's the important part that I like to ask on quizzes, right? If there are only 2 levels of an IV, you will not see Mauchly's test, okay? So when there are only 2 levels, you cannot calculate the variance difference scores more than once. So you have 1 minus 2 and the variance, but then that's it. You can't do 1 minus 3. So there's nothing to compare against. So there's one correlation between 1 and 2, and one variance difference score between 1 and 2, and there's nothing to compare them to. So when you see that there is no Mauchly's, you haven't done something wrong. It's because there are only 2 levels. Okay? So we already have a participant number, so we're going to move on. Now the hard part. We have to switch from wide to long format. And this is the gross part for repeated measures two-way designs. Okay, so we're going to use a reshape, and we're just going to go ahead and melt everything the way that we've been melting. Okay, so I'm going to load the reshape library. And then I'm going to melt that data set. I'm going to leave my ID as my subject number or participant number that we were using before, and my measured are all of those columns. Now what that does, oops, I don't know what I'm hitting that's running everything, so let me just, that graph. I'm hitting some magic combination on my keyboard that makes it run everything. Now let's look at those names of the no-out data set. I used that to create this long data, so really this should be up here. Okay. Now, I'm going to change the column names of my long data so that I just know what they are. So right now I have subject, variable, and value. Right? Variable here is the name of the conditions, value is their rating. So I'm going to change this to subject, temp, and you'll see why in a second, and then rating. Now the biggest problem here is that this temporary column has all 4 conditions in it. And if we ran that as one IV, we would be ignoring the structure of the data where there are 2 IVs. Okay. And so what I want to do now is create 2 new columns. And there's a couple ways to do this. We're going to use the repeat function, but there's also a generate levels function that if you were Googling how to do this, you can find. And we're going to create 2 new columns. And to do this, you kind of have to look at the pattern of the data. So for forward strength, I have low, high, not ho. So low, high. And the n is 157 because I have 1 outlier. So I need to create a column that says low 157 times, high 157 times, repeat. So we're going to use the repeat function, which works by doing the thing that you want to repeat, so the label, comma, the number of times you want to repeat it. So if you do repeat x 5 in R, what you'll get is 5 x's. So I'm going to come over here, and what I've done is for this new forward strength column that I'm creating, I'm going to tell it to repeat the word low 157 times. Then repeat the word high 157 times, repeat low. So I've concatenated that whole thing together, combined it. And what that's going to do, if I come back and look at the long data, is it's going to take this forward strength low of my little code here, so FSG low, and it's just going to put forward strength low into a separate column. So I'm going to just kind of scroll down till it changes and make sure my change matches. So forward strength high is high over here. Flip through some more of them. Forward strength low, low. So you're just kind of making sure that your labels ended up matching what the condition name was. Now we're going to do the same thing for backward strength. Now remember that these two should not be the same. Because otherwise they're essentially going to be perfectly correlated and the whole thing will blow up. So when you're doing this, the 2 different IV columns will have different repeats in them. Okay. And that's essentially what this says. Now what we want to do is break apart backward strength. Backward strength is listed as low 157 plus 157 times. And I figured that out by a little bit of having done this before and a little bit of brute force labor. So I scrolled down to 157 because that's where forward strength changes, and I saw that backward strength didn't change. So there are 2 sets of 157, which 157 plus 157 is like 300 something. So I'm gonna go down to 300 something, and now I can see backward strength high changes at 314. Okay. So it's 157 plus 157. When I add that column in, I'm going to go back down to 314 just to make sure that I did it right. Yeah, so backward strength changes from low to high here, and then it changes from low to high given this code here. So essentially what the purpose of this part is to break that 1 column that's a condition label into 2 separate IVs. Okay. And something that I don't have here in the notes that you can do, so I'm going to add this now, is you can run a table of those 2 columns and make sure, if I can spell this correctly, that there are 100, n number of people in each condition. So I can just run a quick little table and go, okay, I got 157 people in all 4 conditions, which is what I was expecting given this is a repeated measures data set. Okay. And that will just help me make sure that I kind of did this correctly, other than like clicking and viewing automatically. The only other thing I did was I factored this because when we created those, I think they came through as character variables, and some things like ggplot and ezANOVA are just not down with character variables, so we just factored them so that now they're factored variables with labels low and high. Okay. All right. Now we're going to load that ez library. And we're going to run the ezANOVA function. So we're going to say data equals data set. Remember, within subject's ID is not participant number in this exact example, it's subject. Let me change that. For our within subjects variables, we're going to use that dot function that we learned in the 2A between subjects video. Open parentheses, the two column names, close parentheses. So this is the weird part about 2A designs, is that it's not a C or a list, it's a dot. Okay. DV equals the name of the DV, type equals 3, so we're all getting the same mathematical type of sum of squares. All right, let's run that. It's going to give me a little warning. That's okay. So there's no Mahalanobis. So you'll notice that before, if you did the repeated measures 1, when you did repeated measures 1, we got Mahalanobis. Nothing happened this time. You didn't do anything wrong. There's just no Mahalanobis to show you because there are only 2 levels. So we're going to actually jump straight into our interpretation here, right? So if levels are greater than 2, you'll check Mahalanobis. And then it just explains those corrections to you again in case you haven't have slept since repeated measures 1. Okay. So now we're going to look at our omnibus, our overall F test. So we're going to get an F test for each main effect and the interaction. So there's going to be 3 of them. We're going to interpret each one separately. And if our interaction is significant, we're just going to do post hocs for that interaction. Degrees of freedom numerator is DFN, or D for the model. Degrees of freedom denominator or error is DFD. F is F, P is P, and hopefully there'll be a little star next to it and it's significant, right? GES here is generalized eta squared. Apparently I've done this in more than one video. Or eta squared, but I would actually recommend doing, Let's see if I can get this to work correctly. GES here, because it's mathematically for double repeated measures, it's not the same thing as a the traditional. I do not know what is happening with my keyboard here. There we go. Generalized eta squared is not the same thing as regular partial eta squared in repeated measures ANOVA. So let's say you did this in SPSS and you did this in R, these would be very different numbers, is what I'm trying to say. Okay. So let's look up here. So I would say that forward strength with 1 and 156 degrees of freedom is 900 points. It is significant with a pretty large effect size. Backward strength of 1 and 156 with 400 points is significant with a medium effect size, and that interaction is a small effect. Okay. And so we would write those up as the traditional APA style. 1 and 156 P, and then I just suggested a change for eta squared here. But very minimally, they should also make sure it's clear that these are partial numbers. Word, quit trying to help me out here. Go. And that correction just stands especially for repeated measures 2 designs. Okay. So we're going to have to run some sort of post hoc effect, and so if you've been watching these, you'll know that I like to make these tables. So we're going to use tapply with this list function of both IVs, so we get the condition means, to create that table. Okay. And so I just pasted those results in here. But essentially what we're trying to do at this point is figure out the interaction. That interaction is significant, so I could run these t-applies to get my means and standard deviations. I could also use t-apply to interpret the levels. There are only 2 levels, right? So I don't have to run any sort of post hoc for these 2 levels for that main effect. So people rated high ones as higher than low, which is good. And for backward strength, people rated high ones as higher than low, which implies that they're doing something that we told them not to do. So in this study, we wanted people to only tell us how many times out of 100, if I said lost, would people say found. And we want them to ignore, if I said found, how many people would say lost, or the reverse, because often those numbers are different. And so what you should see is that forward strength affects their ratings, but not backward strength. And what we're finding in our study is that for high backward strength pairs, that is influencing their ratings, even though we might have given them instructions to not let that influence their ratings. Okay. But now we just want to see the interaction. So how much is that backward strength impacting things, right? So we did this point. We can just run those t-applies on the main effects, but we have this 2x2 ANOVA, so we have 4 boxes to consider. Remember, I can go across or down, but I should not do both. And so I'm going to pick a direction and split on it. Okay. So what I did was split on forward strength. So for low forward strength items, what is the effect of backward strength? For high forward strength items, what is the effect of backward strength? So here I'm really interested in, like, what is it that people are doing with BSG that they shouldn't be because we told them not to. Okay. All right. And so all I've done here is type in those means and standard deviations. Remember that N here is the same number, they're the same people in each box. I just put it in there to match the rest of the videos that we've done. Right. So now we're going to calculate our post hoc test and our post hoc correction. We're using pairwise t.test, right? But we're going to use paired equals true because we should do a dependent t-test because this is a repeated measures ANOVA. Our p-adjust method is our correction, and we're going to use Bonferroni. Okay. Be sure you use your new split data sets. So I'm going to split here on forward strength. So I'm going to make myself 2 little mini data sets, one for forward strength low and one for forward strength high. I'm going to run my pairwise t-test on those new data sets. Remember, t.test is dv, comma iv. So we've got backward strength here. Right, so don't split and then run the analysis on the split variable. So be sure you split on one and analyze on the other. So let's see what that looks like. So for backward strength on low forward strength ones, there's a significant difference in the ratings, and also the same thing for high forward strength ones. Okay. All right, so skip all the way down here, get down here to p-values. So let's do our interpretation. Our interpretation is that both of these are significant at p less than 0.05. And for high backward strengths, they're rating them as higher than low backward strengths. So there's a 6-point difference here when forward strength is low. And I don't know why. Because when forward strength is low, it shouldn't matter, right? We should rate them the same. Now when forward strength is high, backward strength being high makes it a 17-point difference. Now, the interpretation is the same, is that high backward strength is rated higher than low backward strength. But man, that doesn't tell me much when it comes to an interaction, right? My interpretation is that they have the same pattern of results. Well, the whole point of interactions is that there are different patterns. So I'm going to add my effect size to show that this piece is a much stronger effect than this piece. And that makes it explain the interaction better. Because right now they're the same explain column, essentially. And so now I want to explain why is the interaction significant. Because if they have the same results, what makes this the interaction? Okay. So this is where differences in effect size can be really useful to help understand that the interaction is a larger difference rather than a switch in sides. So it's not like one went up and the other went down. So we're going to use d.dependent.t.average to calculate this. And we're going to put in mean 1, mean 2, SD1, SD2, n, and then alpha, which we are setting as 0.05. You can type these manually, or you can save them using tapply and pull the numbers automatically if you want. I had already typed them manually. When you run this, scroll up a little bit, you want this d value here. So that first difference is a medium effect size at 0.46. And that second difference is a large effect size at 1.47. Right? So what's happening? What makes this an interaction is that at low forward strength, it's a medium effect. At high forward strength, the effect triples. And so that's what this part talks about here, essentially, is that the interaction is occurring because the strength of the difference is bigger for high forward strength than low forward strength. Okay. blah, 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 ggplot, blah, 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 stuff you've seen hopefully a bunch of times at this point. So I'm not going to walk through each piece, but if you need it, I am going to change this to cleanup, just so that we're not calling, saving the name of something as a function name, yada, yada, yada. So if you need more on ggplot, you can read through this or watch the videos on how to fix all these things in ggplot. So we should end up with this kind of picture here. Okay. So we're in my cleanup code, just create the graph. And these graphs are the same double bar graphs that you can find in the original ggplot videos and between subjects, because as long as the data is in long format, the graph is made the same way every single time. And I made it pink for fun. Okay, so we can see the interaction better here. The difference here on this low side is smaller than the difference here on the high side. So this is why a picture is much more useful. And remember that if you put your split variable on X and your analyzed variable on the legend or the group or fill option, that will allow people to compare the bars directly. So you did a t-test of these two and then these two. Okay. Now for the write-up, I've got an example of the write-up here that walks through how to write all of these things together. And the only thing I might tell you to change is my eta squareds here. That needs some updating. But remember, you want to always have 3 F effects, significant or not. So it's very tempting to, when writing these up, if some of the main effects are not significant, is just say it's not significant, period. But remember that when you make a statistical claim, you need proof, so that people can decide for themselves whether or not they believe you. So you're going to want to say forward strength was not a significant main effect and include your F, P, and eta. So always include all 3 F effects for 2 main effects in the interaction, even if you're not going to analyze the main effects. Then follow up that interaction or those main effects with your pairwise t-tests with a correction, and include an effect size for those t-tests so that we can especially help explain this type of interaction where it's in the same direction, it's just a different strength. Okay. So altogether, that is repeated measures ANOVA, doubly repeated designs, going from power, data screening, analysis, through write-ups.